accessing the internet. Let's take a common user like Bob, and let's say that Bob is trying to get to www. and some web server out on the internet. Now, whether Bob's connected physically with a cable or if Bob's computer is using wireless, his traffic is going to go through a switch. Now, a switch operates at layer 2 of the OSI reference model. And just from a nice, clean perspective, here's the official OSI reference model, this stack here. We have the TCP/IP protocol stack, which we use, but when we talk about the layers of the protocol stack of TCP/IP, we actually borrow layer 1 and 2 from the OSI reference model. We call the network layer layer 3, the transport layer layer 4, and then the application layers, which is layers 5, 6, and 7 from the OSI reference model, we simply call the application layers. And that's going to be really important as we discuss some security devices and where in the protocol stack they operate. So from a switch perspective, the switch is forwarding frames based on layer 2 information, and there is some security that we can do at that switch. For example, we could do something called port security. And port security would say on a switch port, okay, I'm only allowing a certain number of MAC addresses into this port. That way, if Bob hooks his own switch to this port and then tries to connect 5 or 6 devices, those devices won't actually make it into the network. So that's what port security can do for us right at the switch. We could also, at the switch, use a technique called 802.1x. And what 802.1x would do for us, it would make Bob prove who he is at the switch before the switch lets his traffic out to the internet even come into the network. So what does that mean to you and I? It means that at the switch, the very first entry point for Bob's traffic trying to get in, we have security measures that we can use on a switch to control exactly who can get onto the network. Now, if Bob's traffic needs to go out to the web server, it's going to have to come off of this local network, and that frame would be forwarded onto a router. Now, a router is a layer 3 device. It makes forwarding decisions based on layer 3 information, specifically IP addresses. And that could be IP version 4 or IP version 6. And the cool thing is that this router, as it's making forwarding decisions for those packets, it doesn't have to allow all packets through. We could have access control lists on that router that say, okay, we're not allowing packets to this specific IP address or from this specific IP address. And that's what makes this device, this router, operating at layer 3, another point in our network where we can control traffic based on rules that we set up. So a router is a layer 3 device making forwarding decisions. So whether it's a lowly Linux box doing routing or if it's a high-end dedicated router, we're going to have the ability, you and I, to say yes or no to certain packets based on the IP addresses involved. Now, by default, most routers don't have any type of control list. They'll simply make forwarding decisions based on what they know, and we can add the access control list to the routers to help restrict what they're willing to forward. Now, presuming that this router is willing to forward its Bob packet out to the internet, we have another device that might be in the path, and that would be a firewall. And a firewall also acts as a router. It's also making layer 3 forwarding decisions, just like a router would, but the firewall has additional intelligence that's going on. What do you mean, Keith, additional intelligence? Well, what a firewall is going to do, typically, is do something called stateful inspection of traffic. And it goes something like this. Bob's traffic, if it goes out to the internet, that firewall will remember in a stateful table saying, oh, this packet came from Bob, these are the ports involved. If it was TCP, it would track the flags at layer 4, and then if the reply comes back from that web server, the firewall would say, you know what, normally I don't let traffic from the internet come into my internal users like Bob. However, because I remembered Bob's connection in my stateful table, and this reply is perfect, exactly what's expected coming back to Bob, I will dynamically allow that return traffic to come back in. And that's what a stateful firewall does for a living. So it's looking at layer 3 to be sure. It's also looking at layer 4 information and possibly higher up in the protocol stack to go ahead and make its decision to allow that return traffic to come back in. So if we put the color codes in, Bob's request goes out, and this pink will represent the return traffic coming back. And the firewall is allowing that pink line to come back in because it's matching the correct parameters. For example, the flags, the addresses, the ports involved that Bob would be expecting as a return. Now, on the other hand, if we had some other device out here on the internet, let's say we take this attacker. If the attacker is trying to initialize a connection going into Bob, the firewall would say, oops, I don't see any requests that Bob had going out to you, and as a result, I'm not going to allow your initial request, Mr. Attacker, to come into Bob. So that's the essence of a stateful firewall, remembering traffic as it goes out so it can dynamically allow the return traffic to come back in. And to do that, it's going to be looking at additional layers of the protocol stack, including layer 4. Now, regarding this firewall, this could be a dedicated firewall device, for example, from Juniper or Cisco or Checkpoint, or it could be a Linux box that has been configured and is running software to properly inspect and handle that network traffic. Now, the question is, okay, Keith, how come we have a router and a firewall? Well, maybe we have the router doing certain functions and the firewall doing other functions, and it's possible to have one single device doing all of your routing and all of your firewall stateful inspection on one device. I just separated them here so I could talk about them individually. I've got a question for you. Let's say the resource that Bob was trying to reach was Google, so www.google.com or just google.com. My question is this: do you suppose there's one physical server for google.com, only one, that supports the entire planet? Now, the answer, of course, is no. They've got thousands and thousands of servers. How exactly do they split up that load? Well, one of the techniques that Google and other companies use to help distribute the load across multiple devices is something called a load balancer. So let's say, for example, Google has 4 servers all running the same content. And let's say all those 4 servers are hiding behind one IP address. So x.x.x.x. So the way it works is Bob does a DNS request for google.com, receives one or more IP addresses, and as he goes to an IP address, that one IP address could be the front end for multiple servers. So for example, Bob's first request may go to this server, and another request that goes to this IP address may go to the second server, and then the third, and the fourth. And it could use round robining, or it can use the least busiest server at the moment. But the key is that load balancer is doing that magic of dividing that traffic across the multiple devices. So some of the benefits of having a load balancer are availability. For example, if there's a lot of people going to that resource all at the same time, because the load balancer is splitting that load across multiple devices, the availability of the response from those servers is going to be greater. And also, if one of these devices failed for some reason and the load balancer was no longer getting a response from that device, it could still do load balancing on the remaining 3, and that would also provide high availability. So whenever there's a need for high availability for a given resource on the internet, it's very likely there's a load balancer involved that can keep that availability for that resource. And besides using load balancers, there's other techniques as well. For example, for DNS, when Bob makes a request for DNS, he could get one IP address back. And when somebody else makes a DNS request, they could get a different response back. And behind each of those IP addresses that are being handed back to clients, there could be a load balancer that's distributing the load across multiple devices. Again, with the goal of providing availability for those clients and customers who are trying to access those resources. Now, one of the questions that you might have is this: okay, Keith, why is it that load balancers are on the list of security devices? And here's why. The 3 major elements of security are CIA, which in this context stand for confidentiality, privacy, so only the right people can see the data that's important, data integrity, which means that data has not been manipulated or changed by unauthorized persons, and then availability, making sure that you can get to your data or your system when you need to. These are the 3 major concepts or ideas in information security. So where the load balancer comes in is the availability. If we have some resource that people need access to, a load balancer can increase that availability, especially when there's large numbers of requests for a certain resource, like a website. So what if Bob is trying to go to a website that he shouldn't be going to? Now, when we talk about shouldn't be going to, I'm talking about corporate policy. Bob has signed an acceptable user policy saying, I agree to the rules. And maybe one of those rules is never go to www.blank.com. I'll let you fill in the blank there. Whatever policy that company has. How do we make sure that Bob doesn't actually go to that website? Well, one option is to use something called a proxy server. So we could have all of our web traffic redirected over to a proxy server, for example. So Bob's traffic would go something like this. Bob would make a web request. His actual HTTP session would go up to the proxy server, and the proxy server would initiate its own connection out to that resource, or try to. So the concept of a proxy server is having somebody else do something on your behalf. Now, Bob may be completely unaware that this game is happening. We've set it up so that all the HTTP requests go out to this proxy server. And one of the benefits of a proxy server is that it can look at all the information up here in the protocol stack. because the entire session is going to the proxy server, and the proxy server is doing its own news session out to the web resource. Because Bob is having to go through that proxy server just isn't forwarding packets based on layer 3 information. It also has an opportunity to take a really hard look at all the details at the application layer, including, for example, what website is Bob trying to go to? And we can have rules on that proxy server that specify what type of websites are not allowed or what specific URLs are not allowed. So the proxy server could monitor and limit access to websites, again, based on the rules that we set up. And a lot of times proxy servers will use some kind of third-party service. So we could categorize, for example, at our company, okay, gaming websites are not allowed. And then when requests come in, the proxy server would look at its database based on the URL, decide whether or not it was a gaming website, and then allow that traffic if it was not a game site. Or if it was a gaming site, it could go ahead and deny that traffic. So the two big benefits there are monitoring at the application layer and also filtering. And that filtering could be called URL filtering, or it could be called content filtering, depending on your vendor and the implementation. And a properly set up proxy server will assist Bob in complying with the rules that the company has set up. So let's say we have Bob still going out to some resource, and let's say this firewall right here is a web security gateway. What does that mean exactly? Well, it depends on the vendor and the features, but basically it means that this firewall has the ability to take a peek at the application layer of what's going through. And let's say that Bob is using HTTP to access some web resource. If this device is a web security gateway, it can be looking at things such as, are these valid HTTP requests? It could be looking at the content and the tags involved inside of that application. In this case, the application being HTTP. If there was some type of cross-site scripting attack that was being attempted, the firewall, because it's looking at that information, could identify it and stop it and not allow that attack to continue. So if there's something harmful going on, or there's improper HTTP commands or HTTP syntax, a web security gateway looking at that HTTP information at the application layer could identify that based on how well the vendor did to implement their solution and then stop it from occurring. And when I say stop it from occurring, this firewall could simply say, okay, to both sides, this session is over. It could close the session. Another common name we'll see for that is an application aware or layer 7 firewall. And again, we're talking about a device that can take a look at the upper layers of the protocol stack to see what the application is doing. In the case of HTTP, valid syntax, cross-site scripting, or other harmful activities that could be going on at the application layer, and then go ahead and stopping it. Next, let's say that we had some users that needed access to the corporate network from the outside world. So their homes, maybe we have Lois and Kevin and Karen and Susan and a whole bunch of other users, and they all need access into the corporate network over the internet. Well, of course, the internet is not a secure place, so what we could do is we could have them build VPN tunnels, virtual private networks, using cryptography and encryption for confidentiality, and we could have all of those terminate at some device in our network. Well, if we had hundreds of people that all needed to connect, we might have a separate device called a VPN concentrator that would be used to go ahead and terminate all those connections. Now, when I say terminate, I'm talking about being the endpoint for all those connections. So we have a dedicated device that's managing all those VPN tunnels, and if the users authenticate and prove who they are and all that good stuff, then the VPN concentrator can go ahead and allow that traffic into the network. But that's what a VPN concentrator is. It's a concentration of VPN connections. And oftentimes it'll be done on a dedicated device called a VPN concentrator, or it may be done at the firewall itself, who's also performing that functionality. Another challenge that every network is going to face is malicious traffic that's going over the network. How do we identify and stop that? Well, one option is we could put a device on the network called an intrusion detection or intrusion prevention system. The biggest difference between IDS and IPS is that intrusion detection, it can see the traffic, it can set off alarms, but it cannot stop the traffic. It seems like a warning system without any meat behind it. An intrusion prevention system has all those same features. It can see the attack, it can identify it, but the intrusion prevention system also has the ability to stop that traffic before it enters the network, hence the keyword prevention. So an IPS. The N portion simply means that we're talking about network-based intrusion detection or intrusion prevention. So an example of intrusion prevention would be, for example, two interfaces. We're going to go ahead and disconnect that there. So all the traffic that Bob sends out to the web server and all the traffic that comes back from the web server has to go along this path. It goes like this, up to the IPS, down through the IPS, and out. If the IPS sees something that it does not like and the rules are configured to drop that traffic, the IPS can go ahead and stop it, effectively not allowing it to make it past, whether it's going from Bob to the web server or from the web server back to Bob. In the case of the intrusion detection system, we wouldn't have two interfaces. We'd have simply like one. We'd copy the data over to the IDS, and then it could send us alarms if it sees malicious traffic. But because the IDS is only getting copies of the traffic, it wouldn't be able to stop the live traffic from going through the network. Now, one of the benefits of using a network-based intrusion detection system or intrusion prevention system is that we can monitor the traffic to websites or the entire company or subnet as opposed to a single device at a time. So if Bob is here and there's 10 other computers here and there's 100 other servers on the internet and we have all this traffic going back and forth, a network-based intrusion detection or prevention system can go ahead and see all of that instead of just looking at the traffic for a single host. We have visibility to all traffic that's going between, in this case, between this router and this firewall. And the next logical question might be, okay, well, what is the option to monitor just a single host? And they call that host-based IDS or host-based IPS. So up here we'd have NIDS for network-based IDS and NIPS for network-based IPS. And in the case of host-based IDS or IPS, instead of having a dedicated appliance like this, we simply install software, for example, on Bob's computer. And that would be called HIDS for host-based IDS or host-based IPS, depending on the function that software was providing. Does it stop the attack, or does it just alarm us the fact the attack is happening? Now, the next question that we should chat about is how in the world does an IDS or IPS system, whether it's network-based or host-based, how does it know whether or not traffic that it's looking at is good traffic or bad traffic? I mean, how does it know? And one method that an IDS or IPS system can use is called signature-based, which is also known as definition-based. And the reason for that is that a signature-based IDS or IPS has a database of specific things that it's looking for. So let's say, for example, we have a vendor like Checkpoint, as an example. And let's say that they have 2,000 signatures in their signature database. All the traffic that's going through the network is being compared against those 2,000 signatures. And if there's a match, then there's an alarm that's fired off, and then based on the rules that are set up, if it's IPS, it may decide to go ahead and stop that traffic to not allow it to continue any further in the network. Or if it's an IDS device, it can fire off on that signature, send an alarm so that we can be notified that this activity is happening on the network. So signature-based is only going to fire off or identify known attacks that match one or more of the signatures in the signature database of the vendor whose IPS or IDS you're using. And that brings us to another challenge. What about traffic that is not in that database of signatures that still may be a problem for us? And that's why we have additional methods that can also be used. For example, we have behavior-based, which can also be thrown into the category of anomaly-based and heuristics. With anomaly, heuristic, and behavior-based, what we're really looking at is a baseline. For example, we might plug in an IPS or IDS device into our network, and it dynamically looks at all that traffic and gathers a baseline. So let's say, for example, ICMP traffic is approximately 0.1% of all the traffic on our network over a period of time. And if that's our average, that could be put into our baseline. And if, for some reason, ICMP over the course of an hour or a day goes up dramatically, let's say it goes up to 10%, that would be considered an anomaly compared to our baseline. So a behavior-based or anomaly-based system would fire off an alarm saying, hey, this is an anomaly, this is a problem, this is not normal traffic, which could alert us to take a closer look at what's going on. One primary method I've seen for anomaly-based is with TCP scans. For example, if a client is going out and looking for a resource, it sends a TCP SYN request, and it should get a SYNAC coming back. So an anomaly-based system could keep track of, for example, what is the average number of half-formed sessions at any given time. And if that number is, for example, 5, we have 5 half-formed sessions at a time, and that's the baseline, and then it goes up to like 100 or 1,000, which is very indicative of something like a worm or some other attack that's happening with TCP scans across your network, The anomaly-based system would say, whoa, here's our baseline of 5, it's up at 100 or 1,000, and it can go ahead and alert us. And if it's an IPS system for preventing the traffic from happening, it can go ahead and stop those connections from propagating through the network. So anomaly-based IPS, it does not need a signature to match on, and the anomaly-based is looking for some type of anomalous traffic pattern compared to the baseline. And a lot of times when people get an IPS or IDS system, they may put it in IDS mode for a while, just so it's passively learning the network to build those baselines without taking actions. And then once they have it all dialed in to reduce and minimize false positives of that system, then they may go ahead and turn on IPS mode now that they're sure what their baselines are and what alarms will be firing off after they've tuned it for their specific network. So as an example, here's Checkpoint's intrusion prevention system. If we take a look at the protections by type and go to signatures, it's going to give us a laundry list of all the signatures, the specific items from a signature-based IPS that they're looking for. I also want to point out that in addition to anomaly-based, just looking, for example, a baseline and then comparing traffic against that baseline, there's also protocol anomalies. So in this implementation, they also have protocol anomalies. Again, an anomaly is something that's happening that's different from the norm. So regarding the protocols like IMAP and FTP and so forth, if there's activity that's deviating from the normal standards for those protocols, this IPS could go ahead and fire off or stop that traffic. And I bring this up because the concept of an anomaly can be from a baseline of normal accepted behavior, or it could be from a baseline of normal network traffic on your specific network. And again, the cool thing about anomaly-based IDS, it doesn't need a specific signature to trigger. It's based on some type of abnormal behavior or unusual traffic based on a baseline or how a set of protocols should operate. Now, one of the challenges in using any type of a network-based intrusion detection or prevention system is that if Bob is going off to a banking website, so he's going off to the bank, he's going to want to use something protected. For example, he'll go to https:// using either SSL or some flavor of TLS. SSL is secure sockets layer and TLS is transport layer security. And what's happening with those protocols is that we're taking everything in the application layer and it's all being encrypted. And that's great, so that as Bob's packet travels to that web server, if anybody does sniffing or eavesdropping on the network, they won't be able to steal confidential information. For example, his login information, or when he's requesting a balance inquiry to see exactly how much money he has in the bank, all of that information is encrypted in the packets as it's being sent. Now, encryption for confidentiality is a great thing. However, if you're an intrusion prevention system or an intrusion detection system, how in the world are you going to analyze the information at the application layer if it's all encrypted? And the answer is